All right, hello everyone and welcome. This week in the Organic Chemistry Lab, we're going to be covering the classification tests for functional groups. So these classification tests are sort of like spot tests, similar to the solubility tests we did in the previous week, I believe it was the first week. So as the name implies, the purpose is to figure out the functional group, or rather to suggest the functional group. So we want to know what the functional group could be, and these spot tests will help suggest what those functional groups could be. So you may be asking, well, if we have IR spectroscopy, which could help us find the functional group, why would we conduct a classification test? These are test tube tests. Well, before the days of NMR spectroscopy and of NMR, which you're learning about currently, they had to rely on IR, and IR wasn't enough. So these spot tests were also considered evidence to help them figure out what the functional group was. So it's always good to have multiple pieces of evidence to support what your unknown could be. So we have three tests for today. We're doing the chromic acid test, the 2,4-DNP, and the bromine test. And very quickly, these three identify certain functional groups. So the chromic acid test identifies alcohols, and aldehydes, and we'll go into more detail about which alcohols. The 2,4-DNP test identifies ketones, and aldehydes. And the bromine tests for unsaturation. Unsaturation meaning double bonds. So double bonds. Okay, so we're going to go over each of these three, and figure out how they work. So the first one we're going to cover is the chromic acid test. So chromic acid, H2CrO4, is a strong oxidizer. So it's an oxidizing agent. It steals electrons. And specifically, the chromium atom has a 6+ oxidation state. So it's lost 6 electrons, okay? And this reagent is capable of oxidizing certain oxidizable functional groups. And as you can see here, we have a little oxidation plot of how carbon is oxidized depending on how many oxygens or what types of oxygens it's bonded to. So if you look in the top row here, we have a primary alcohol. So this is a primary OH. Primary meaning it's connected to a carbon, one carbon connected to a primary carbon. And you can see in red here it has 2 alpha hydrogens. This is the alpha carbon, therefore these 2 are alpha hydrogens. If you oxidize this alcohol here, you remove one of these H's and then you get an aldehyde. So this is an aldehyde here. So you've gone up in an oxidation state. If you oxidize this again, oxidize the aldehyde, you end up with a carboxylic acid. Okay. Going in the reverse direction would be considered reduction. Okay, so this is for a primary alcohol. So a primary alcohol can be oxidized one step up to the aldehyde and then another step finally to the carboxylic acid. That's the most oxidized form of carbon, besides CO2, CO2 being the most. For a secondary alcohol, you can see that now instead of having 1 alpha hydrogen, we only have, 2 alpha hydrogen, as in the primary alcohol, we now have 1. And when you oxidize this, you end up getting a ketone. Okay, so this is a secondary alcohol because it's connected to a secondary carbon. Notice the 2 R groups, those are carbon fragments. And the resulting functional group is a ketone. Okay, so notice we can only go up 1 oxidation state because there's only 1 alpha hydrogen. Okay, and the reverse direction is reduction. For a tertiary alcohol, these groups cannot be oxidized, because they do not have alpha hydrogen. See, notice that they have 3 R groups and no alpha hydrogen. So tertiary alcohols will not be oxidized by chromic acid. So chromic acid can oxidize these groups. So it can oxidize primary alcohols, secondary alcohols, and also aldehydes. So we have a little chart here depicting how that works. We have a primary or secondary alcohol or an aldehyde, any one of these 3. If you mix it with chromic acid, you'll end up getting a carboxylic acid or a ketone, and you get some chromium byproducts. So the way it works is you basically put some of your unknown here. You don't know if it's an alcohol or an aldehyde. You put it in a test tube, and then you mix it with some chromic acid, the reagent. Sometimes it's referred to as Jones reagent in honor of the chemist who devised this test, Jones reagent. And this reagent is red. So chromic acid has a very nice red color when chromium is in its 6+ oxidation state, so Cr+6. Now, when the chromium is oxidizes this, the chromium itself is reduced, so it stole the electrons, and in doing so, it forms these new chromium 3+ ions. So now instead of it being chromium 6, it's now chromium 3. And these compounds range from blue to green. So to detect for a positive test, if you mix these two together, your unknown and chromic acid, and you observe that it goes from red to blue to green, you can conclude that there may have been an alcohol or an aldehyde. So that's sort of how the test works. The mechanism is pretty neat and worth going over. So let's start with a primary alcohol. So say we have an alcohol. Okay, so here's our alcohol. I'll draw one of the alpha hydrogens here. Okay, and we're going to mix it with some chromic acid. So chromic acid is very acidic. Here's the Lewis structure. Now in solution, because it's very acidic, it's likely that this OH group will be protonated. So now we have a good leaving group. So what can happen is this alcohol will attack the chromium, just like that, and then the water will leave. Okay. Now we generate this product. So now the chromium is bonded to this oxygen. Now there's going to be a series of proton transfers. So there's going to be a base. It's probably a little bit of water in the Jones reagent. It's going to take that proton away and neutralize the charge on the oxygen. So now we're going to have, maybe I'll redraw it this way. Okay. Now the oxygen is neutral. And then here's the punchline, if you will, the most interesting step. Now another base, most likely water, is going to steal one of the alpha hydrogens. So this is how the alpha hydrogen is removed. It will deprotonate that. These electrons between the hydrogen and the carbon form the carbonyl carbon here, okay? And then these electrons leave with the chromium, okay? By the way, this species here is sometimes referred to as the chromate ester, because it sort of resembles an ester group. So you have, this is sort of like a carbonyl, and then this is like OR, of an ester, okay? And in doing so, now we form an aldehyde. Okay, so this hydrogen was from here, it just wasn't drawn. So there were two hydrogens, one of them left, and now you're left with one. Get your aldehyde. This chromium byproduct looks something like this. OH. It has a pair of electrons sitting on the chromium. And here the chromium is in its 4 oxidation state, +4. This eventually degrades into its +3 oxidation state, which gives you the blue color. But the mechanism there isn't too concerning. What's interesting though is the aldehyde will not stop there. So in the presence of chromic acid, aldehydes will not stop their oxidation. They'll go straight from primary alcohols to aldehydes and then finally to carboxylic acid. So how does that occur? Well, aldehydes, when you have water in the solution, especially if it's an acidic solution, exist in equilibrium with their hydrates. So if this is protonated, the carbonyl, it makes this carbon very electrophilic. So this water molecule could attack, push electrons up. Okay, I guess it's better to put some equilibrium arrows. Okay, so there's our OH group there. Here is our protonated water that attacked. Okay, here's the hydrogen there. And then we can do another proton transfer to eliminate the charge on oxygen. So return these electrons to oxygen, okay? And now we get a species that looks like this. Okay, this species is referred to as a hydrate. And you can see that it sort of resembles an alcohol. So it has an OH group, it actually has 2 of these OH groups, and it has an oxidizable hydrogen. Therefore, we can continue oxidation. So it's more of the same. We start with our hydrate. Okay, one of these alcohols is going to attack the chromium. Okay, and as we know, this is probably protonated. It's a good leaving group. Okay, so alcohol attacks chromium, this leaves, and it gives you another chromate ester. For the sake of time, I'm not going to show this deprotonation. We'll assume the proton hopped off onto another water molecule. Okay, here we go. So now we're ready. This is another chromate ester. And now this chromate ester is ready to eliminate. So we take another water molecule. It's going to attack the alpha hydrogen. Okay, these electrons form the pi bond between the oxygen and carbon. And then this leaves. And then it forms the chromium byproduct. And the resulting species, if you can see here, so is this. Now it's drawn a little awkwardly here because the carbonyl is pointed down, but this is now a carboxylic acid. Carboxylic acid. Okay, so now you can see how aldehydes become carboxylic acids in the presence of chromic acid. So pretty neat mechanism with this chromate ester. This step is very interesting, how it steals these electrons. The second test we're going to go over is the 2,4-DNP test. So 2,4-DNP is an acronym, stands for 2,4-dinitrophenylhydrazine. So this group here is the DNP. This is DNP. So it's a benzene ring. It has this group here. When you have two amines bonded together, that's called a hydrazine. So if you have 2,4-dinitro, so this is the 2 position, it's 1 carbon away from this carbon, and then 4, so 2,4-dinitrophenylhydrazine. Phenyl refers to the ring. Okay, so this DNP group will actually react with carbonyl compounds. So the question we're asking ourselves is there a carbonyl? And it's, well, as you'll see, it's only certain types of carbonyls. And the certain types are ketones and aldehydes only. Only these two, ketones and aldehydes. It will not react with amides or esters or carboxylic acids. And that's because those other functional groups are not very electrophilic at the carbonyl carbon. They have stabilization from resonance. So this test will only detect ketones and aldehydes. And you form this functional group, this compound here, and this compound, the functional group here is called a hydrazone, sort of like a combination of hydrazine and ketone, if you will, so hydrazone, okay? And these compounds tend to be red or orange or yellow, and they tend to precipitate. So that's an indication of a positive test. That's what we're looking for, the formation of this product. And it will only form in the presence of ketones and aldehydes. So let's go over the mechanism. So if we have I'll choose a ketone, but it could be an aldehyde. So aldehyde would be if this was an H. The mechanism is a little less involved than the chromic acid mechanism, just a lot of drawing. So you have your nitro groups here. Okay, this nitrogen here at the terminal end of the hydrazine is fairly nucleophilic, so it can attack this oxygen, and it's probably protonated in solution. There's a little bit of acid in this DNP reagent, so it's probably protonated. Okay, the resulting species looks something like this. So here we go, that's the OH, so the electrons went up to oxygen. Here's the nitrogen bonded to it. Okay, and then here's our benzene ring. Okay, this oxygen is probably protonated again. There's some acid in solution. Okay, and this will generate a good leaving group here, so you'll see that. Okay, so here's our water, good leaving group. Here's our nitrogen. I'm going to draw the lone pair because that's going to be important. Okay, here's our nitro groups. Now this step is the punchline of this mechanism, if you will. Now this is a good leaving group, and we have a lone pair here. So this lone pair can come down, form a pi bond, a double bond between carbon and nitrogen, and it will kick off the water. So the water will leave. Good leaving group. The resulting species will resemble our hydrazone. So here we go. Double bonds, nitro group. Okay, and now this nitrogen has a positive charge, and the only thing left to do is to deprotonate it. So water probably picks this up, and the resulting species is our hydrazone. Excuse me, yes, it's our hydrazone. Oops, it should be a nitrogen. H. Okay, there we go. There's our hydrazone. So that's the mechanism of it forming. So this reaction generates water. It's a byproduct. You should keep in mind these sort of mechanisms because the carbonyl chemistry in the second semester is very interesting and very important for the lecture. So the act of a nucleophile attacking this carbon, pushing electrons up, and then you protonate this alcohol to get water. The water leaves and forms a new sort of carbonyl compound, a new double bonded carbon species. So pretty cool reaction. Okay, so now let's cover the bromine test. So this is the final test we're going to be covering, the bromine test. And the mechanisms for this test you'll see are redundant, so we're not going to go into the mechanisms. You've seen them, EAS for example, but we'll get to that. We covered last week. And double bonds you covered in the first semester of organic chemistry. So for the bromine test, what we're looking for is there a presence of a double bond? Is there unsaturation? And if so, if there is a double bond, what is the type of double bond? So this test we can sort of tune to discover what kind of double bond it is. Well, if we have an array of different double bonds here, and we'll cover what occurs. So bromine, molecular bromine, is red. So keep that in mind. The bromide ion, though, when it's ionized and when it reacts, this is colorless. So one indication that this bromine test is positive, in other words, there was a reaction, is if it goes from red to colorless. That's a good indicator. The other good indicator is that you get a white precipitate. So bromides tend to be insoluble. Precipitate, make sure I can spell that. They tend to be insoluble and they tend to be white solids. So if you see the generation of a white precipitate in your reaction, it suggests that this was a positive test. So these are the two things we're looking for. Let's go over each of the different double bonds that can react with bromine. First, we have a plain double bond here. It's typical alkene, linear. When it reacts with bromine, if you remember, it forms the bromonium ion and then the bromine attacks it. So you get a bromine here and a bromine here, and you get this species here. And this is a positive test. So this would probably be one of the white precipitates in the test. So if there's an alkene, it will react with the double bond, a simple alkene. Something interesting happens, though, if you have an electron withdrawing group connected to this double bond. So this has to be physically connected to the sp2 carbon here. It can't be far away. If it's connected there, this electron withdrawing group will actually withdraw electron density, making this double bond less nucleophilic. Less nucleophilic. So at room temp, these tests are typically done at room temperature. At room temperature, there is no reaction here. So this is not nucleophilic enough to react with the bromine. However, this gives us some insight. If we didn't know that this was an electron withdrawing group, say we had some compound, and we noticed it didn't react with bromine, we could try to heat it. So sometimes this is done by heating it with a blow dryer or putting it in a hot water bath. And if it reacts then we can suggest that there was a double bond, but it's a special type of double bond. It has an electron withdrawing group. So in the presence of heat, electron withdrawing groups do tend to react with bromine to give you products. So that would be another observation. We need to heat it in order for it to work. The last scenario is if the double bond is in a ring. So if your ring has an electron withdrawing group, this tends to be more nucleophilic. And these tend to react at room temperature. So these rings will react with bromine through an EAS reaction like we covered. So this ring will attack the bromine and probably put it on the ortho or para position. I've just drawn it on the ortho position here. And as a byproduct, though, we generate something special. We generate HBr gas, which, as you know, is an acid. So another way we can test it, say we had two alkenes, if we just placed one of them, or say we had two unknowns, and we placed them in two test tubes, and we did the bromine test, and they both tested positive. Well, that's an issue, right? Because we can't distinguish them, right? They're both done at room temperature. They're both done with bromine. Well, one way we can distinguish them is by putting pH paper in the headspace above the test tube. So if you take some pH paper and say put it here, kind of hang it on the edge here, the HBr gas will sort of turn it red here. And the idea is that if you do detect HBr gas, so if yes, we get HBr gas, we can conclude that there's probably an EAS reaction going on. And if this EAS reaction is occurring, we can conclude that there was a double bond, but that double bond was in a ring. And that ring probably had an electron donating group, making the ring more nucleophilic. So these are the different scenarios here. We're going to show you some known compounds in the lab, in the experimental, and it'll give us a good idea of what to observe in a positive test. And I've summarized these sort of results in this table, which I'll put on Canvas. So we have these different tests here. So these are our oxidation tests and DMP tests, and then these are our bromine tests. So we can quickly go over them here. You can skip this if you'd like, but I'm just going to go over him here to summarize. So for the chromic acid test, the positive test observation. So if we have a positive test, this is what we will observe. That's what this row represents. So, and this test is the conclusion, how we interpret the positive test. So in chromic acid, what we look for is a red to green. So we start with red and it turns to a green or blue color, or you get a green-blue precipitate. So that suggests that the chromic acid was reduced. And if that's the case, it's a positive test, and we can conclude that there was probably a primary alcohol, a secondary alcohol, or an aldehyde. Okay? For DNP, if we observe the formation of a yellow, red, orange precipitate, that suggests the presence of a carbonyl. Only certain types of carbonyls, though, only ketones and only aldehydes, only these two. For the bromine test, if we observe that there was a red to colorless transition, so the bromine was consumed, that's what it represents, or the formation of a white precipitate, we can conclude that it's a positive test result. And that suggests that there was a double bond present. If we needed to heat the tube in order for the bromine to react, that suggests that the double bond is connected directly to an electron withdrawing group. And finally, if we detect pH paper in the headspace of the test tube, we can probably conclude that there was an EAS reaction taking place. So that double bond was part of an aromatic ring, and it probably had an electron donating group. So all of these things together allow us to sort of decipher what the unknown has in terms of functional groups. In other words, to classify them. Okay, hope you enjoyed that, and we'll see you in the lab. All right, so we're in lab now. We've got our test tubes. So these are test tube tests. The first set of tests we're going to do are our chromic acid tests. We're going to go in the same order. So we've got 5 tubes here. One is going to be our control, and we're going to test 4 different compounds. And we're going to 4 known compounds, and we're going to observe what we should see in a positive or negative case. Okay, so what I'm going to do is I have some chromic acid here. This stuff's pretty corrosive and also carcinogenic. I didn't mention it in the pre-lab, but this chromium in this oxidation state in 6+ is sometimes referred to as hexavalent chromium, and it's a known human carcinogen, so not that pleasant stuff. So you should be careful, try not to spill it anywhere. So what we're going to do is we're just going to add some to these vials. These vials have some acetone in it. Acetone is the solvent, and it's important to use reagent grade acetone because some acetone is contaminated with perhaps a little bit of isopropanol, and that isopropanol will give you a false positive. So you need to use the pure reagent grade acetone here. Okay, and we're just going to add some to each of these. So we'll just add a little bit. You don't need very much to each test tube. Place that aside here. You can see that it's got a little bit of turbid because the chromic acid is probably forming some chromium salts that are not soluble in the acetone. But what we're looking for is from a transition from red to blue to green. So this is our control here. So you can see, looks all the same. So it's just all acetone and chromic acid. So let's go through our unknowns. We'll start with butyl alcohol. So this is N-butyl alcohol. So N-butyl alcohol, so this is a primary alcohol. So our expectation is since it's primary, it has alpha hydrogen and therefore it will react with chromic acid. So grab a little bit, you don't need very much. So I'll hold it up like this. Okay, we can add some. Okay, you can see already there's a little bit of a green there. And if we agitate the solution, you can see that the red color has pretty much disappeared. And now it's a grayish green-blue. Okay. And if we agitate the test tube even more, you can see the precipitate. So these are the chromium salts. It's like a water complex with the chromium. And it indicates that this is a positive test result, which we know, right? It's a primary alcohol. Okay. So that is N-butyl alcohol or 1-butyl alcohol. Now let's do 2-butanol. So this is a secondary alcohol, and our expectation is that this will also react with chromic acid because it has 1 alpha hydrogen, so we can still oxidize it to the ketone. Okay, so here's our 2-butanol tube. We're going to add it here. Okay, see, you can see a little bit of color change. We keep agitating. There we go, green. So another positive test result. All right, this test tube is a little bit different. This time, we're going to use the other isomer of butanol, tertiary butanol. So tert-butanol, this is a carbon with 3 methyls and 1 OH group. So there are no alpha hydrogen. So this is, we predict that it will not be oxidizable. Oops, it's a little stuck here. It will not be oxidizable. So when we add it, we expect there to be no color change. It will remain the same. It should look identical to the control. So here's our tert-butanol. Okay, and if we agitate, yep. So no matter how hard I agitate this, it will not react. Okay, it's still red. So if we compare it, So on your left is the control, acetone and chromic acid. On the right is tert-butanol and chromic acid. No reaction as well. It looks pretty similar. A little bit darker, but it's pretty much the same. It's negligible. And then here we have a positive test result. This is what it would look like if it did react. So you can see it's like grayish, bluish green. Okay. And the final test is we're going to do an aldehyde. So as I said before, aldehydes will react with chromic acid because they have an alpha hydrogen and they form hydrates in solution. So you will still get a positive test result with an aldehyde. The aldehyde we're using is a p-anisaldehyde. It's a benzene ring with an aldehyde attached and a methoxy group. And it smells similar to star anise, the spice. Okay, so if we take some of the aldehyde, drop some in. These may react a little slower. Okay, it's a little difficult to see, but there is a hint of green to this solution compared to our negative result. Sorry, let's compare it to the control. Yeah, so you probably wouldn't be able to tell. If you just looked at that, it would be kind of hard to decipher if that's a positive or negative because it's not very blue. But when you hold it next to your control, you can definitely see that there was probably a reaction that took place. So there is some precipitate. It looks a little grayish, bluish green. And the solution above the supernatant is a little darker green too. So they just react a little bit slower, but nevertheless, it is still considered a positive test result. Okay, now we're going to move on to our DNP tests. All right, now we're going to do our DNP tests. So this is the DNP solution, 2,4-dinitrophenylhydrazine. It's an orange solution. There's a little bit of it that's solidified in the bottom. For this test, you cannot use acetone as a solvent because acetone obviously is a ketone and the ketone will react with DNP. That will give you a false positive. So we can't use acetone as a solvent. Sometimes ethanol is used as a solvent, but for our purposes, we can actually just do it solvent-free. We can just mix this reagent with the compounds directly. So I'm going to add some to 3 test tubes. We're going to test 3 compounds. So add a little bit, add a little bit, add a little bit. There's a little bit too much in that one. All right, so we've got 3 test tubes. We're going to test 3 samples. The first one we're going to do is our p-anisaldehyde, the one we just did. So aldehydes will react with chromic acid, but they will also react with 2,4-DNP. Okay, and remember the positive test result we're looking for is the formation of a red to yellow to orange precipitate. So this is our p-anisaldehyde. Okay, there you go. You can already see it's a very fast reaction. Okay. There you go. Don't even need to agitate it. You can already see that there is a positive test. So orange precipitate, kind of like a pumpkin, Halloween orange, compared to the pure reagent. So you can definitely see a difference there. Okay, so this was our p-anisaldehyde, knowing that aldehydes react. Okay, now we're going to try a ketone. So this one will be acetophenone. We've actually got, let's see, we've got, where is it? 4-methyl acetophenone. So it's a benzene ring with a ketone, but there's a methyl group. The methyl group doesn't interfere with it at all. So we're just concerned with the ketone group. Okay, so we'll take our test tube. Yep, and as you can see before, it looks exactly the same. We see a positive test result. So nice orange solid. Okay, the final one we're going to do is a little bit of a negative control where we know there's going to be no reaction. So I've taken our, let's see if I can find, here we go. This is the nitration product from the previous lab, M-nitromethylbenzoate. So this is an ester. It's a nitro group, there's a nitro group, but we're concerned with the ester. Now ester is a carbonyl functional group, but it does not react with 2,4-DNP. So when we mix the solid with this DNP, we expect there to be no reaction. So we'll take a little bit of our product. I'll just use a little pipette to grab some solid. Okay, we'll add it. Okay. And as you can see, no reaction. You basically just have a suspension of this solid in the DNP. There's no orange color change. So esters, and for that matter, amides and carboxylic acids do not react with DNP, only aldehydes and ketones. Nice. Okay, so the final test is going to be our bromine test. Okay, all right, the final test we're going to do is our bromine test. So we have 4 test tubes. One is going to be our control, and they all contain DCM, the solvent. So the reason DCM is used as a solvent is because it's inert, does not react with bromine. Bromine is very reactive. And here's the bromine reagent. It's not pure bromine, it's fuming a little bit, but it is bromine dissolved in dichloromethane. As you can see, it's a nice red color. So what we'll do is we'll add some bromine to each of these. Okay, so a little bit in there, a little bit in there. Nice. Okay, so here are our samples made up. So you'll see that's a nice red color. A positive test result is indicated if this red color disappears and or there's a formation of a precipitate. The precipitates tend to be solids, white solids. So we have our control. So this one we'll leave alone here. We're not going to do anything to it. It's just going to be DCM and bromine. The first test we're going to do is with cyclooctene. So cyclooctene is a 8-membered ring, and there's a double bond in it. So that double bond is unsaturated, and it will react with bromine. So if we add a little bit, we expect the color to disappear. Cyclooctene is very smelly, so good thing we're doing this in a fume hood. It's not very pleasant to smell. Okay, so got some in there. So when we add it, you should see the red color start to disappear. Maybe I'll add a little bit more. Okay, this looks kind of old for cyclooctene. It's kind of viscous. Anyway, so there we go. A little bit of agitation, and you can see the red color has disappeared. Nice. So positive test result for cyclooctene. Place that one in the back. Okay, we're going to get set for the next one because it's going to require some heating. All right, so now we've got our dimethyl malleate to consider. So our dimethyl malleate is a double bond, and you'll see the structure here. It has electron withdrawing groups on it. So those electron withdrawing groups will withdraw electron density from the double bond and make it less nucleophilic. So at room temperature, we expect it not to react. So take our pipette here. Oops, this pipette is a little broken. Got our test here. Okay, so I put a generous portion inside there, and as you can see, no reaction. If I agitate it, it lightens a little bit, but if we compare it to our control, it looks about the same. So control on the left, dimethyl malleate on the right. However, if we apply some energy to it, so this is a little cup of hot water, beaker of hot water, and we place it inside, maybe I'll agitate it a little bit. Okay, fairly slow reaction, but I think we can see a difference now. So there you go. So this is probably the hardest test to interpret because these are very similar, but nevertheless, the dimethyl malleate tube is a little lighter in color. It's more yellow than red, and this indicates that some of the bromine was consumed. So if there's a consumption of bromine, that means that there is a double bond present, and we needed heat. So that tells us that there's an electron withdrawing group on there. So yeah, hardest test to interpret. So positive test, but difficult to observe. The final test is going to be an EAS reaction. So we're going to take guaiacol. Where is it? Here we go, guaiacol. Guaiacol is 2-methoxyphenol. That is by the way, the standard or the the framework for all of the vanilloids. So depending on what you place on that ring, on this ring, you can get vanillin or eugenol, as we discussed in earlier labs. So this one smells nice too. It kind of smells like a cross between vanilla and caramel. By the way, the OH and the methoxy group are electron donating, so they make it more nucleophilic, this ring. So the reaction should go very quickly. So take a little bit of our guaiacol. It smells rather nice. Put some in the test tube. Place that there. And there you go. You can see that almost immediately color has vanished. So almost all the bromine was consumed. There's perhaps a tinge of yellow in here, but clearly you can see it's a positive test result. We went from red to colorless, right? So if we compare our bromine tests, so on the left is your control. So just DCM bromine. On the right is the dimethyl malleate. So this is the one with an electron withdrawing group, needed heat. And then we have our guaiacol. So this was an EAS reaction. Now, if we wanted to detect if it's an EAS reaction, one way to tell is if there is HBr gas in the headspace of the mixture. So what we can do is we can take some pH paper. This is just universal pH paper. What we're looking for is orange or red. That indicates the presence of acid. So we'll take a little strip. If I can get it, here we go. Need a longer strip than that. Okay, we'll bend it a little bit, and then we'll place it in the headspace of the test tube. We'll agitate it. It probably works better if you put this in immediately as you react it. Okay, so we've made up a new test tube here. So this is DCM and bromine. We're going to redo the test, so we're going to add some guaiacol, and I'm going to quickly add the guaiacol, and then add the pH paper very quickly. So it's a different pH paper. Sometimes they don't last too long. So there's our guaiacol. Okay, so lightening in color, and there we go. So this pH paper is much better. You can see the transition between red and orange. So if you do a bromine test and you observe that it will change pH paper red, that indicates the presence of HBr. And if there's HBr, we can suggest that the double bond that's substituting is existing within an aromatic ring, and that ring probably has a donating group. Okay, so if we compare our samples here from left to right, so left is our control, right is our dimethyl malleate, and then here is our, so this one needed heat, and then this is our EAS reaction with the guaiacol. Nice. So hope you enjoyed the lab, and you can use these observations to help you with the quiz.